Welcome to a review session for exam number 1 for ECE 501B. I want to first give you a quick rundown on the process, the material that will be covered, and then the type or style of questions being asked, and then we'll quickly go over some of the topics that run through the material that you should be expected to know for exam number 1. The process is listed here. You will have 2 sheets of notes. Those are normal size sheets, 8.5 inches by 11 inches, but you can put material on the front and back of each of those sheets. You can bring a calculator and something to write with, but that's all you should be bringing to the exam are 2 sheets of notes, a calculator, and something to write with. You won't be allowed the textbook or any class notes, no cell phones, and no computers. The exam is scheduled for Wednesday, the 2nd of October, and you will actually have 75 minutes to finish the exam. The material that you will be expected to know comes from the Axler book, chapters 1, 2, 3, and just barely into chapter 5 down to the bottom of page 79. The structure, as I just said, you will have 75 minutes for the exam. There will probably be 5 questions. Some of those questions might have multiple parts. There will probably be at least one proof, demonstrate, and some other questions might have you demonstrate or show or produce counterexamples based on definitions, propositions, theorems, or corollaries, or you may need to create or build something that's related to this course. For example, vector spaces, subspaces, direct sum, decomposition of a subspace, the basis, know what that means, know how to use that to build a basis for a given vector space, or a subspace, know what a basis of a subspace looks like or how to build one. Matrices, how do you create a matrix representation for a linear map? Once you have these linear maps, when is a map injective, when is it surjective? And finally, into chapter 5, we start looking at how to find eigenvalues and eigenvectors for linear operators. Another place that you can refer to for the style of questions would obviously be the homework problems that have been assigned during the semester so far. Let's now quickly go through the topics, and this will really be a walkthrough of the material based on the textbook material. And we start with chapter 1, where we start with vector spaces. And remember that the vector space really has 3 features. It has some set of vectors, and that vectors is in quotes. That's not necessarily restricted to the normal linear algebra vectors. Then that set of vectors needs to have the property of vector addition, and that to be a vector space, that addition needs to be closed to vector addition, and it also needs to have the property that it's closed to a scalar multiplication. Though that's sort of the general way of thinking about a vector space, you also need to be able to work with the definition of a vector space, maybe the when is a set a vector space, what are some properties that a vector space needs to hold, and those are the 6 properties. You need to have commutativity, associativity, you need to have an additive identity, we need to also have an additive inverse, we need to have a multiplicative identity, and it also has to have this distributive property, must hold. You also should be able to provide examples of vector spaces, or Y is a subset not a vector space. You should be able to identify the properties that it's not satisfying in order to violate it being a vector space. You also need to be able to work with subspaces of these vector spaces and what properties need to hold in order for a subset to be a subspace. It has to have the additive identity element. It needs to be closed under addition and closed under scalar multiplication. Those 3 properties, because it inherits all these other properties from it being a subset of a vector space, to verify that a subset is indeed a subspace, you really need it to have these 3 properties. In chapter 1, we've also talked about, or didn't restrict attention to just looking at finite dimensional vector spaces, and you should be able to work with both infinite dimensional vector spaces and finite dimensional. Obviously, we in this book start restricting our attention to finite dimensional vector spaces, and that's chapter 2, which really means that we have a finite number of coordinates in these vectors that we are using to represent these vector spaces. Once we've now restricted our attention to something being finite dimensional, we can talk about the span of a vector or a set of vectors. We can also hopefully show or prove that a set of vectors is or is not linearly independent. If you have a set of linearly independent vectors that span a particular space, then that particular set of vectors could be used as a basis. And I've said this is now plural because a set of basis for a given space is not necessarily unique. We can also count the number of linearly independent vectors to obtain a size or a dimension of that vector space. And as I said before, you need to be able to deal with vectors being independent or when are vectors dependent, and this you need to be able to work with abstract vector spaces in addition to the typical linear algebra vectors that you might be used to thinking about. Once we have this space defined where we're living in terms of where these vectors are coming from, then we can look at Chapter 3 material, which talks about linear maps, meaning once we know where these vectors are coming from or live, or once we have defined a space for vectors to live in, then that opened up the additional information in Chapter 3. Now we started examining ways or linear maps for moving back and forth or moving between these vector spaces. If we are looking at linear maps, we might refer to that as a linear map T going from an input vector space V to an output vector space W. Then in order for this map to be a linear map, we need it to be satisfying a couple of properties, namely additivity and homogeneity. And that then allows us to conclude that this map is linear, but you need to be able to contrast that with maps that aren't linear, or to point out when you might have a nonlinear map. Once we start playing with linear maps, one of the first concepts that we learned about was what are the vectors in the input space, let's say V, that actually might map into the zero vector in the output space, meaning there might actually be a non-trivial subspace in the input space V where vectors live, that any vector in that particular subspace gets mapped into the zero vector in the output space. And we saw this close correlation between maps that are injective or one-to-one in this concept of null space. An injective map is when you have, let's say, a linear map operating on U, and that actually is equal to the same linear map operating on V. Then if we have an injective map, then that implies that U and V, the input vectors, were actually identical. And a simple picture that you could think about in trying to understand an injective map might be this one-dimensional diagram, in a sense, where X is your input space and your vertical direction is your output space. If a horizontal line only intersects that map in one place, then you have a one-to-one mapping between the input space and the output space. The relationship between injective maps and null space are that if you do have an injective map or a one-to-one map, then these injective maps actually possess a trivial null space, or the only vector that maps into the zero vector is the zero vector in the input space. Meaning that might be helpful in certain constructions or verifications. If T is an injective map, or if you're trying to show that T is an injective map, then can you show that the only element in the null space of that map is the zero vector? Then you know that that particular map T is an injective map. The other thing that you need to remember is that the null space of T, or the vectors that live in the null space of T, are coming from the input space, or the domain of our spaces involved with that linear map. Once we learned a little bit about null space and injective maps, then we started talking about the range of maps, or where in the output space can you get to when you map through this linear map T, or you might see me abbreviate that as script R of T. That's now this, all the set of output vectors W, such that for any input vector in the input space, what are all the possible output vectors W that you can get to? Then you have this additional property relative to the range of a map. If the range space of a linear map actually equals the entire output space, then that's what we call a map T when it's injective. I'm sorry, is surjective. Or when the map is onto. And another way you might think of that is the range of T covers all of the output space W. And a quick picture for that might be that if the vertical axis again is your output space W, and the input space is the horizontal axis, then you need to be able to get all of these real values in a one-dimensional output space covered by this mapping. And pictorially, then you might see that you're going to every point in this output space W is mapped onto from points in the input space V. We can then combine both of those mapping properties. If T is one-to-one or injective, and onto or surjective, then T is an invertible map. And once you have an invertible map between any two subspaces, then those two subspaces are similar in behavior or in properties. And we call that isomorphic. If there exists an invertible map between two vector spaces, then those vector spaces are isomorphic. Or those two vector spaces are what you could think of as similar. Once we have these invertible maps, these isomorphic vector spaces, then we started looking at the matrix representation of these linear maps. And those matrix representations, those depend on the basis that we're using for the input vector space and the output vector space. Something that you can quickly start using if somebody now gives you a couple of vector spaces and asks if the linear map between those is injective or surjective, then if you go from a larger vector space to a smaller, and here the larger to smaller just has to be of 1 dimensionally. If you go from a large input space to a smaller output space, then you can immediately conclude that your map is not injective. There's no way that it can be 1-to-1. There's a non-trivial null space. If you have the other situation where you're going from a smaller vector space to a larger vector space, then you can immediately say that your map is not surjective. Again, if we're moving between an input vector space that's the same as the output vector space, then that's called an operator, and we simply say then that T is an element of this operator or this linear vector space V, where V is both the input vector space and the output vector space, and T is then an operator, which maps back into the starting vector space. So V is really itself, and you could even just say, you know what, let's just have these linear maps now starting in the vector space V and ending in the vector space V with the appropriate vectors. Once we have these operators defined, or in matrix representation, these square matrices, now we can start talking about invariant subspaces and a class of invariant subspaces that we have gotten to so far in the beginning part of chapter 5 are these eigenvectors, so that you now have this ax is equal to lambda x, meaning you operate on x by a linear map in a matrix representation A. That vector through that linear map gets mapped back onto that same vector, which is a very specific operation property of that linear map A. And these eigenvalues and eigenvectors will provide us with useful properties. And right now what we want to be able to do on exam number 1 is actually use those. Or I should say be able to find eigenvalues and eigenvectors for fairly straightforward matrix representations, let's say A. And you might also want to know, is it actually possible given a linear map for eigenvalues to not exist at all, or for some eigenvalues to exist, but in terms of numbers, may be much less than the dimension of the vector space that you're operating on. And in particular, what you'll want to be able to do is look at when your field of numbers is equal to the real line, or when your field of numbers is this complex field. And you're pulling now your coordinates and your scalars from either R or C. That has a big influence on whether or not you do or do not have eigenvalues for specific matrices or linear maps. I think I've said this earlier, but let me just repeat it, and that's what I'll finish with, is in terms of the material or the content, you will be responsible for everything in Axler other than Chapter 4 up to the bottom of page 79, which is starting into the first part of Chapter 5. Hopefully that gives you a very quick overview of the course. Chapter 1 through Chapter 5, or part of Chapter 5, and you can start to now put all of these ideas into play and understand how they are all connected. Starting with where these vectors begin in vector spaces, restricting those vectors to be finite dimensional or have a finite number of coordinates or entries in a vector. Once you have that, now you can talk about span and linearly independent vectors. How many linearly independent vectors do you have in a given subspace? That'll give you the dimension. What's this relationship? Can you find constants, non-zero constants, which will allow you to combine vectors to produce the zero vector in a vector space? Then you have linearly dependent vectors. How do you map between vector spaces? That's chapter 3. And for linear maps, you need additivity and homogeneity. Once you have these linear maps, you can talk about the null space and the range space, whether those maps are injective maps or surjective maps. If they're both injective and surjective, then this linear operator is invertible. And once it's invertible, then you can go back and forth between these two vector spaces, or these two vector spaces are similar or isomorphic. It'd be nice to be able to create matrix representations of these linear maps, and that depends on the basis. You should be able to build up a matrix representation of linear maps given a set of basis vectors. If you're going from a larger vector space to a smaller vector space, then you have a non-trivial null space and the map is not surjective. If you're going from a smaller to a larger, then there's no way that you can cover that larger subspace or vector space, and so your map is not surjective. Finally, then, when you are going from your input vector space, mapping that through a linear map back into the same vector space, now we're dealing with an operator, and we can then look at invariant subspaces of these square matrices, and that then allows us to define eigenvalues and eigenvectors, which provide us with a very clean way of producing invariant subspaces for given maps. Hopefully that gives you a big picture view of what you will be needing to know on exam number 1, and now you simply need to put down the details or the specifics relative to the questions that are asked. Good luck.